Hi everyone, welcome to CHEM. Now today's video is on term symbols, and here we are going to deal with the different types of interactions which are necessary in order to generate the term symbols. Now before starting, there are a few videos uploaded in the channel about the coordination chemistry. You can watch it. I will give the link in the description box as well as the I button present above this video. And for this video, you need the knowledge of different quantum numbers which we have already dealt with in atomic structure videos. Those videos link I will also give in the I button as well as the description box. So let us start. Now certainly when we talk about the quantum numbers, we know about orbital quantum number, magnetic quantum number as well as spin quantum numbers, and those were generally applicable for one electron system. But when we shift to a particular system where there are multiple electrons, these quantum number fails to justify their functioning. As a result of which, we generally consider combination of different type of quantum numbers, and that combination is generally focused as interactions. The angular momentum of orbital and spin motions in many electron atoms can be added in many ways, and those ways we will see. The interactions which we were talking about are mainly of three types, where we will deal with spin-spin coupling, secondly orbit-orbit coupling, and thirdly spin-orbit coupling. Each of these three we will deal with in details. So first we are going to deal with spin-spin coupling. Now in this case, from here only you can understand that spin-spin coupling refers to the spin quantum number of each electron. Now the electrons present in the multi-electron system has particular spin of its own, either plus half or minus half. So if we add up those spins, we get a specific coupling number, and this is known as resultant spin quantum number, which we represent generally with a capital S. What is the range of this quantum number? The range is certainly from S1, S2, summation of the whole number of spins present up to the depreciation of the all spins present. That is, we will consider all the ways of electron to be arranged in a particular configuration. Once we deal with an example, it will be easy for you to understand what is meant by spin-spin coupling. Now in this case, it is present that there is a formula for this one which we can write as S, capital S, is equal to summation of Si. That is, number of spins, different spins are present in different electrons, we will add it up. First we will deal with one of the examples. Let us see. We will deal with P2. So first write down the configuration of P2. Here we have p orbital. One electron can be upspin, one electron can be again upspin. Similarly, we can have another configuration where we can have one upspin and one downspin. This is also possible. So from here, if we try to find out the total spin S, for this electron we have plus half, for this electron we have plus half. So this is half plus half. We are getting it as 1, and for this one we have plus half, for this one we have minus half. So we get it as half minus half is equal to 0. So for P2 configuration, we can have two possible S. One is 1, another is 0. This is how we can take out our spin-spin coupling constant. Another example, if we see for d orbital, we have d5. So if you try to calculate d5, there can be maximum number of electrons which is unpaired is 5. So for 5 electrons we have half spin. So we can write it as 5 by 2. Now decrease one of the electron and pair it up, we will have one less. So the total minus 1. Again decrease 1 from it, so you will get half. Now if you try to decrease 1 from it, you will get a negative, which is not taken into consideration as we are taking modulus value. If you try to check it with the electronic configuration, try out for this one. Here you can see half plus half plus half plus half plus half. There is 5 unpaired electron. It will be 5 by 2. Similarly for this one, 1, 2, 3, 4. So 4 unpaired electron in the up spin. So 4 into 1 by 2, it is 2 minus half. You will get 3 by 2. Similarly here, because half minus half 0. So for these two we are having 0 and for this one we are having half. Try out for D4. It's easy. Just like the previous one, you can write down as 4 by 2. Now 4 by 2 becomes 2. Next you will do is what? Decrease one value. So it will become 1 and again minus 1 we will get 0. So these are the probable values of S, that is spin-spin coupling number. Now in the next part we are going to deal with orbit-orbit coupling. Now we have already seen in our previous video that in atomic structure there is one quantum number which is known as orbital quantum number. So for one electron system we were comfortable with only one L value. But since here we are dealing with the different number of electrons, as a result here we are having a summation of this thing and it is written as capital L and it is summation of I, L, I. And again you will add up all the things, then start decreasing one from each. So if we start with again P2, let us see for P2. Try out. For P2 you have blanks like this. So see here, generally we have one electron here, another electron here. And the value of L corresponding to this one is +1, 0, -1. Now the capital L will become +1, +0, 1. Right? Similarly, if you try another way, that is, if you arrange the electrons in +1, 0, -1 and the two electrons present here, then you will get L equal to 0. Similarly, another way is take this one and arrange it, one here, another again here. So there will be L equal to 1 plus 1, you will get 2. So what are the values which you obtained is 2 minus 1. So it is 1 and 1 minus 1, 0. So these are the values of L corresponding to P2. Now we will see for D2. So if we consider D2, then try to draw. There are 5 suborbitals. So here we have +2, here we have +1, 0, -1, -2. First always take the most stable one. So this is 1, this is 2. So for this one you have L equals to 2 plus 1, which is equals to 3. Now if you try to put the two electrons in the first one, then this will be the maximum, as a result of which you are getting another value as L equal to 2 plus 2, which is equals to 4. Once you get 4 and 3, you can write down the other values, which is 2, 1 and 0. So these are the values corresponding to D2 configuration, right? So these L values will help us to understand what is the characteristics of spectroscopic lines of the corresponding orbitals of S, P, D and F. When you have previously, you have already seen that when you have ML values of 0, 1, 2, 3, 4, 5, the orbitals were S, P, D, F, G, H, I. And now when you have the capital L value or ML value as 0, 1, 2, 3, 4, 5, the corresponding energy states are going to have the naming starting from S, P, D, F, G, H, I. This is generally our L, which we will see in the term symbol. This represents the L. From here only, we will understand what is the term S meaning. So if you see here S actually denotes singly degenerate. That is, there is only one state and there is no ways to exchange energy. P term refers to triply degenerate. Next, if we go for D, it is 5-fold degenerate. And for F term, you can write as 7-fold degenerate. So these are the ways of spin-spin coupling, and now we had learnt about orbit-orbit coupling. Last one which we are going to deal with is spin-orbit coupling. So spin part is our S, orbit part is our L. So when we are coupling these two, we are performing LS coupling. This LS coupling gives rise to another quantum number or another coupling constant which is known as J coupling constant. This is very important. So the value of J generally lies from L plus S, and then we are going to decrease one by one. Ultimately, the last one which we are going to get is L minus S value. So if you try to do, previously we had already done the P2 ones. So you have seen the P2 values of S as 1 and 0. L value you have already seen as 2, 1, 0. So first, if we try to take the value as 1 and 2, then L plus S for 1 and 2 will become like this. J equals to, you can have 3, decrease by 1. So you will have 2 and you will have 2 minus 1, which is 1. This is the last one, which is L minus S. No more subtraction. Similarly, if you consider another combination where S equals to 0 and L equals to 1, J can become 1 only. And 1 minus 0 is also 1. So this is how you can take out the J. Now if we talk about the term in the word term symbol, then the energy levels which are characterized by certain values of capital S and capital L are called terms. And the coupling which we have already seen is LS coupling or Russell-Saunders coupling. And when we are talking about the term symbol, what is the way to represent the term symbol is very much important. So in this case, the way to represent the term symbol or the Russell-Saunders term symbol is given by 2s plus 1 Lj. Now S value we can obtain easily. So 2s plus 1 is the spin multiplicity. From here we can obtain easily the 2s plus 1 value. L is the state which we have already seen previously, which is S, P, D, F, G in the capital letter, and J is the value which we obtain from L plus S coupling. So these are different kinds of states of energy, and if we try to find out that a particular term symbol consists of how many number of such different states, it can be easily found out. From L and S value, if you want to find number of microstates from L and S value, you can write it as 2L plus 1 into 2S plus 1. Or if you have in your hand the value of J, you can easily find out by using another formula, that is 2J plus 1. This is another formula which you can use. Now, we have already seen the 3 types of coupling. There is one more coupling which is known as JJ coupling, which occurs in the heavier atoms, and it will be dealt in a short way. You will see the next video on that. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.